Let us wait for a few more minutes until others join. Okay, let us start. So we discussed stress, normal, shear, and we discussed continuum hypothesis in the last class. We said that here we will assume any fluid substance, a domain of fluid, to be made up of a continuous material. Okay, that is known as continuum hypothesis. So it is a continuum. We are not taking it as something made up of individual molecules which are discrete in nature, because we cannot differentiate, we cannot apply differential calculus there. So it will make the maths complicated, and we will have to track individual molecules. So it will be a very difficult task to track all the molecules in a substantial amount of fluid. So that's why we assume it to be a continuum. But can we apply this continuum assumption everywhere for all kinds of fluid mechanics problems? So let us take an example here. We can apply continuum hypothesis to water flow, even to air flow. Let's say this is Earth. Okay. Let's say this is the exosphere. Okay. Till where there is the atmosphere. Okay. After that, there is no atmosphere. Okay. There is a loose boundary. This is Earth's atmosphere. And there is vacuum outside. So there is a region here where the mean free path is of the order of meters. It can be even kilometers in some region between vacuum and the atmosphere of the Earth. So you might have watched or heard about this, that um, someone jumped off some rocket or some spaceship, okay, from the outside of this atmosphere or very close to the outside of the atmosphere, okay, and fell from there, had a free fall from there. One such name is Felix Baumgartner. Okay, he jumped from there. Also, these spaceships, reusable spacecrafts, they use something called a re-entry vehicle. So the rocket carries this re-entry vehicle in which passengers go to space station, and then the re-entry vehicle comes back into the atmosphere. So all of this has to be designed for thermal loadings, also the atmospheric forces and all these things. So you have to predict in advance the forces that the atmosphere will apply, the drag force, the pressure, all of these things. How fast will the re-entry vehicle approach the atmosphere and so on. So a re-entry vehicle looks something like this. This is the upper cap of this entire rocket. You might have seen a rocket. Something like this. Okay. So there are different stages in this rocket. Okay. And these are different fuel tanks or individual rockets attached to this bigger one. Okay, there can be several things like that. So this is the re-entry vehicle part, the upper part. Rest of it is just fuel tank. Okay. So this is where the payload goes. So the people are inside this re-entry vehicle. It goes there and it comes back. There's a shock wave that forms in front of this re-entry vehicle. Okay, when it approaches the Earth. All right. So can you apply the equations of fluid mechanics that we'll be studying in this course, assuming that the material is continuous? Can you apply it here, near the boundary between the vacuum and the atmosphere, or in the outer atmosphere? So because the mean free path is so much that for a 1 square meter area, for a 1 square meter cube volume, you have only a few molecules of air. So clearly, you are still not in the continuum regime. This is, let's say, the density that we plotted the other day, and this is the volume of this cube. Still, you are somewhere here. So volume is very low, so that the density is not clearly defined. The density is fluctuating a lot. Maybe it is zero sometimes when there are no molecules of air inside this volume, and sometimes it is more, and so on. And after some limit, the continuum limit may have some other volume. Okay, this volume limit for the continuum assumption to be valid may be 1 square kilometer. For some region in the outer atmosphere. Okay, but your re-entry vehicle may not be that large, of the order of kilometers. it is of the order of a few meters, right? So you cannot apply the continuum assumption. You cannot assume the air to be continuous medium in this region of space. Okay. But as it comes towards the earth, as the air gets denser and denser, this limit may be 1 meter square or 1 centimeter square, and then ultimately 1 millimeter or micrometer square. Oh, sorry, this is cube because we are talking about volume. Okay. So then close to the earth, this assumption is valid. So they have to use molecular dynamics in the extreme outer atmosphere. Then in between, some mesoscopic methods where the number of molecules are so large that molecular dynamics will be very intensive. It will take a very long time to solve those equations, even on very advanced computers. So there are methods in between, for example, discrete Monte Carlo or uh, lattice-Boltzmann methods and so on. So these are known as mesoscopic methods, like lattice-Boltzmann method or discrete Monte Carlo, which we'll be not getting into. This is just for some information. And microscopic molecular dynamics. We'll just write the short form, molecular dynamics. And what we will be studying in this course, macroscopic. This is the continuum hypothesis. And in that, the equations that you get finally, they are known as Navier-Stokes or modified Navier-Stokes, or in general, mass conservation and momentum conservation. So I'll just write Navier-Stokes equations. This is not a method, these are equations as opposed to the other two, molecular dynamics, LBM, DSMC, these are methods. Navier-Stokes are equations or continuum methods, you can call them. Okay. Any question up to this point?
No, sir.
Okay. So close to Earth and for fluids that we will see in our everyday life or in industries, you can use continuum assumption. That is sufficient. Okay. So we discussed the stress strain rate relationship. What happens here is, let me write the equation for fluid mechanics in continuum sense. So let's say this is a pipe and some fluid is flowing through it. Now we will compare this method that we are going to use in fluid mechanics with what you already know for solid mechanics. Let's say there is a ball in solid mechanics. What you do is some force acting on this ball F and given mass, you can write force equal to ma, mass times acceleration. Acceleration you can write as derivative of velocity with respect to time, dv by dt. And then you can integrate this equation to calculate the velocity of this ball. Okay. Integral f dt by m. Now you can also calculate the position of the ball by integrating this again. You can write dv as ds by dt, which is displacement, equal to this integral f dt by m, and then you can integrate it again to calculate s. So that's how you calculate position and velocity of a ball or a solid particle. Now what happens in case of fluids? Let's say initially when the fluid is not moving in this pipe, we consider a region of fluid enclosed in this rectangle. Now after some time, when the fluid is flowing, what will happen here is, what will be the shape of this rectangle after some time? It will be very different from a rectangle. Why? Because we saw that there is no slip condition on the walls of a solid. The velocity profile, we discussed that it looks like this. Okay. At the center of the pipe, velocity is maximum. As you go close to walls, it becomes very less, and at the walls it is 0. Now you can see that the particles that lie in the center of the pipe will move ahead of the particles that are close to walls. So after some time, this would have deformed to a shape. Let me draw it in some other color. Right?
Yes, sir.
Something like that. And you can imagine the complexity when this pipe has bends or has a turbine or a pump. Then what will happen to the shape of this domain? Now, if I tell you to apply this force equal to mass times acceleration for this patch of fluid, for this volume, for this fixed mass, which is moving in time and space, it will be very difficult to track this mass. In solids, it is very easy. For particles, you can track a ball. The particles are not deforming with respect to each other. But here in case of fluids, it is very difficult to track the mass of fluid. If you had to track this mass of fluid, what you will have to do is calculate the force on this boundary. On this boundary, you have to find the forces. All the forces acting on this boundary. And when the boundary deforms, then for the new boundary, you have to calculate all the forces. So it is very difficult to do that. Why? What are the forces acting on this? The forces are the stresses. So you have to separate this mass as a free body. Okay. And then the outer fluid, that is another body. Okay. So just like we did for solid bar, so we had a single bar, let's say some forces were acting on it. What we said was, let's say you take a section and you separate both of these to analyze them, to analyze the force at the cross section. So you have a force here. Let's say we take them apart, not physically take them apart, but just for the analysis. So to balance the force on the left hand side, there must be some force that the other block is applying on this first block. Let's say this is the first section, second section. So the second section is applying some force on the first section at the cross section that we have taken. So this is the force, and equal and opposite force must have been acting on the second piece, which is that one. So this is free body diagram, free body analysis. This gives us the force at this section. Let's say this is AB section. This is the same section AB. This is also the same section AB. In case of fluid, we cut the fluid domain into two parts. This is the first domain, and this is the second domain, the outer one. What is the force that is acting between first and second? There are internal stresses, internal forces. What kinds of forces? There can be pressure applied by the second fluid on the first fluid. By the first fluid on the second fluid, there will be pressure. And other than that, there will be viscous stresses. Because of viscosity, because there is relative motion between these two fluids, this layer is trying to move, or this layer is not trying to move because it is in contact with the solid. So this has lower velocity. This fluid has higher velocity. So there is some force between these two layers. So there is a force acting here. There is a force acting at each and every point. Some force, okay? So this force you need to determine for this moving domain. Like this, as it deforms continuously. So this is a very difficult task. We don't want to do this. Therefore, what we'll do is we'll try some other method. Instead of tracking a fixed mass of fluid, let's say this is the pipe again, what we will do is we will create a fixed volume in space. Can all of you hear me?
Yes, sir.
I think there was some issue with the network.
Yes, sir, we can hear you.
Okay. Yeah. So what we'll do now is we'll consider a fixed volume in space. We are not going to track a fixed mass of fluid as it moves through this pipe. We are going to consider a fixed volume, which I have marked by this blue box. And we will observe the fluid that is coming into this volume and the fluid that is leaving this volume. Okay, this fixed volume in space. We do not care which particle goes where. We just care about with what velocity the fluid is coming in, with what velocity it is leaving this box, how much fluid remains in this box, how much is going through its boundaries, all of these things. And how it simplifies the problem is that we will have to take care of the forces acting only on this box always. The force can be changing in magnitude, in direction, on the boundaries of this box, but the boundaries remain fixed. So this simplifies our problem. We don't have to change the boundary every time. So this is also known as control volume analysis. And the previous approach is known as control mass analysis. There we have a mass, fixed mass, that is also known as control mass, which is moving through space. But here we have a fixed volume, which is known as a control volume, and we will be looking at only at this volume. So now we have to write the laws of physics for this volume. What are the laws? One of the laws is conservation of mass. It says that whatever mass goes in to this volume has to either come out or get accumulated inside this control volume. For example, you have a tire tube, tire of a car, a bike, a cycle. When someone fills in air inside that tire, what happens is in that control volume, this is the tire control volume, and there is an inlet. So the air is going in through this inlet. Let's say m mass of air goes through this inlet. Then you are sure that if there is no leakage in this tire, then m mass of air is inside that control volume, right? That is conservation of mass. So, yeah. So basically, mass that goes in is equal to mass that goes out. Let's say there is some leakage and some mass has gone out. Then you know that the mass that has gone in is equal to mass that has gone out plus the mass that is inside that has been accumulated in the tire, right? That is simple. So this is called mass conservation law. But often we don't want to deal in total masses because we have to tell the time also here. In time t, this is valid. So for time equal to 0 to some t prime, this is valid. So you have to calculate m in for time 0 to t prime, similarly m out from time 0 to t prime, and m accumulated from time 0 to t prime. So after that much time, you have to note all these values and put in this equation. If we want to express this at every instant of time, what we can do is differentiate this equation with respect to time. We can also say that the rate of mass going in, dot means rate, which is also dm in by dt. So the rate of mass flow in is equal to rate of mass flow out plus the rate at which it is getting accumulated. All of you may know this already. Okay. How can we write this in terms of the other known quantities of the fluid, such as density, viscosity, velocity of the fluid? We are denoting velocity by u vector, so we'll use that. Pressure in the fluid and so on. So what is rate of mass flow in? Let's see that for this pipe. This is the inlet. Okay. Velocity into dt or delta t. In time dt, what is the volume that goes in? So velocity times dt gives the distance which a particle in the fluid travels, right? So let me draw it here. Let's say you have velocity u in this direction. And so you know that in time delta t, it travels delta x. Then what will be delta x in terms of velocity and delta t? It has to be velocity times delta t, right? So speed times time is the distance. And what will be the volume of fluid that goes in or that passes in this much time? It has to be area of cross section A times delta x. So let me write dx here. I am using dt and delta t, dx and delta x interchangeably. This is not correct maths, but still I am writing it like this. Okay. So u dt dx, that is what? This is the volume flow rate. Actually not flow rate, this is the volume, the total volume that goes in time delta t or in time dt. So let me call this volume passing any point or any cross section A in time dt. Sorry, there is some problem here. So I have written dx here. U dt was equal to dx or delta x, and then times A gives us the total volume that passes through this area of cross section A in time dt. Now what about the mass? Because we are writing in terms of mass here. What will be the mass? It will be the density at that cross section times the volume. So now this entire thing gives me the mass of the fluid passing through cross-sectional area A in time dt. Is that clear? Is there any question about this? I can repeat
No.
this if it is not clear.
Yes, sir. It is clear.
Okay. Fine. So we'll go ahead. So we have done this for the inlet. This is the mass that is coming in. Similarly, what will be the mass that is going out? It will be again this velocity at the outlet. So density at the outlet. So this is at the inlet. Velocity at the outlet, time dt, cross-sectional area of the outlet. And what is mass accumulated in the control volume? What is the mass of the control volume? Mass of the control volume is rho times the volume of the control volume, which is fixed. So that is very easy for us in this control volume analysis because the volume is fixed. what is the volume of this control volume? So just let us say that it is capital V. So d by dt of rho V, where rho is the density inside the control volume and capital V is the volume of this control volume. Now you can see some problem here. The problem being that the density can vary inside the control volume itself. It can be a function of space. So what we need to do to write this equation accurately is that we need to write it for a point, mathematical point, or the control volume which is very, very small, so that the density does not change in space. So we'll write this assuming that this V control volume approaching 0, so that it is very small. Okay. Let us assume let's say this is x-axis, this is y-axis, and this is z-axis. Let's say this is delta z, this is delta x, and this is delta y. This is our control volume, which is very, very small. Delta x, delta y, delta z approach 0. What is the area of cross section of this left face? Let's say this is delta x times delta z for this face. So let us substitute it in this equation here. For the left face, area of cross section A is delta x, delta z. So density rho U. Oh, just a minute. What we have done here is on the left hand side, there is a mistake here. We have written the mass passing through cross section A in time dt. We have not written the rate of mass flow. So if you want to write the rate of mass flow, not the actual mass that flowed in time dt, what you do is divide by dt on the left hand side. You take a derivative with respect to dt. So this dt goes away and you get the rate of mass flow instead of the actual mass passing in time dt. So we will write the rate, and on the right hand side here we have written the rate of mass change. If we wanted to write the total mass change or mass accumulated, we would have written dt here. So the rate multiplied by the actual time passed. So this dt cancels out from here and you get rho u A. A is delta x, delta z. For this left face, if you want to write the mass that goes in from the bottom face, that also we can write. The area will change. It will become delta x, delta y, and it will be the vertical velocity there. Right now, this u vector that we have written, this is the velocity in the horizontal direction. Okay. So this one, and then you have equal to rho u delta x delta z out, because there also the area of cross section is same, delta x delta z at the outlet here, if we are writing it only for one dimension right now, and plus you have d rho v by dt. Now what is the volume of this control volume? Delta x delta y delta z. Now because delta x delta y delta z all are fixed, it is a fixed control volume, it is not deforming. We can cancel out delta x delta z from both the sides. Okay, and we can take delta y to the left hand side, we can divide throughout by delta y, so this becomes rho u in minus rho u out by delta y equal to d rho by dt. And of course we are talking about a very small control volume, limit delta y tends to 0. But please note one thing, that we have done this only for one component of velocity, which is the horizontal component. Assuming that all the flow is like this, in this y direction. If we consider all the other directions, then we will get here plus rho u in delta y delta z, okay, and rho u minus delta y delta z out, and so on, all of these things. We will go to a complete derivation, but right now you can see that we have derived the mass conservation law in terms of velocity, density, and the derivatives of density and velocity. We will write the formula after we have gone to some other details. So we have not derived it fully here, but finally it will look like this: del dot rho u equal to d rho by dt. Okay, which we'll learn very soon. Okay, so that was the power of control volume analysis. Solving this equation, you will get the velocity of the fluid at each and every point. Because we have done this for each and every point now, we assumed that the control volume is very, very small. So in this pipe, we assume the control volume to be very small, somewhere here, let's say, or it can be somewhere there. And it is very small such that it is actually a point. So this differential equation that we wrote finally, del dot rho u equal to d rho by dt, it is actually valid for a small point. So you can find velocity if the density is known at each and every point of this pipe. Here we have not assumed that the density is constant, we have assumed that density can vary in space and in time, and velocity is also not constant throughout the cross section. We have not made any such assumptions, so it is a general equation for any kind of fluid flow. But this doesn't solve our problem. Let's say density is fixed or varying. Let's say it is fixed to make things simple. The formula that we get is still del dot u equal to 0. If you write it in a scalar form, if you expand this, you will get dou u by dou x plus dou v by dou y, dou w by dou z equal to 0. Here U, V, W are velocity components in x, y, and z directions. Now you have three unknowns, U, V, W, and only one equation. So you need more equations, you need more information. So we'll go to the other equations that we need to solve this fluid flow problem in the next class. But from here, you can notice a few things. If, let's say, it is a one-dimensional flow, velocity in y direction is 0, z direction is 0, or not changing, then the formula is dou u by dou x is 0, or u is a constant. So if it is a one-dimensional flow along a line, then the velocity has to be constant along x. It is not a function of x. That is what it means. It can be a function of y or z because it is a partial derivative with respect to x. So a function of y and z at most, or a constant. So in this pipe flow problem, this is a pipe. If you have velocity u here, you will have the same velocity u along this x axis. That is what it gives. So this gives us the volume conservation or mass conservation formula or equation. Is there any question up to this point? Is the maths understandable? How many of you know this partial differentials or differentiation, integration? Can you please raise your hands, all of you? How many of you do not know? Let me ask it the other way. How many of you have problem with these kinds of expressions? Okay. And some of you somehow have both. Either you have problem or you know it, but I don't know. Okay. So I assume all of you understand this. Okay. Fine. So if you have any question, you can ask, or you can send a mail, and I'll send you some video lecture or something else, which can make it more clear for you. Okay. Thank you.
Sir,
Yeah.
will you send some recorded lectures for this week?
Yeah, I'll send that. I did not upload the last recorded lecture. So I'll upload all of these live lectures as well as the recorded lecture on that YouTube channel.
Okay, thank you, sir.
Yeah. Thank you.